Okay, as we already discussed that the paramagnetic materials are those materials in which the atoms have their own dipole moment. Suppose this is a paramagnetic material and these are the atoms inside this material. Now these atoms are randomly have their own dipole moment, but they are randomly oriented. These are the direction of dipole moment of individual atom. Now if we increase if we apply an external magnetic field to this material, suppose this is the direction of magnetic field, then the dipole moment of each atom ally itself in the direction of magnetic field. So these are the new direction of dipole moment of each individual atoms. Similarly, we also discussed that the dipole moment, the orientation of the dipole moment depends on temperature. By increasing the temperature, each atom gets a certain amount of kinetic energy, due to which the atoms move up, down, or left, or bottom, or in any direction. Okay, so due to which the orientation of dipole moment disturb, and as a whole the net dipole moment of the material decreases. This was all about what we discussed in the previous video about paramagnetic material. Now likewise Langevin diamagnetic equation, Langevin also derived an equation for the paramagnetic material which discuss all the properties of paramagnetic material, and he consider a diamagnetic material as a classical It discussed the paramagnetic material by using the classical approach. He assumed that the atoms of the diamagnetic materials behave like a paramagnetic gas. The material, paramagnetic material behave like a paramagnetic gas. Magnetic gas, in which each particle of the gas, has its own magnetic moment, magnetic dipole moment. This was the approach of Langevin for the paramagnetic material. Now if we have suppose we have a atom and which has its own dipole moment mu m, magnetic dipole moment, which is whose direction is shown here. Now if we apply a magnetic field to these atoms B, then this magnetic dipole moment makes an angle theta with the magnetic field. Now once the field is applied, there is a torque on this dipole moment, due to which it rotates its position in such a way that the atomic dipole moment, which is this one, now parallel to the magnetic field. So the potential energy, which I will represent by E of the atom in the presence of magnetic field, is given by this relation we already derived it, minus mu m dot B, or E is equal to minus mu m B cos of theta. This is equation number 1. Now if we calculate the small change in potential energy due to a small movement of this dipole moment, like from this position to this position, can be calculated by differentiating this equation. dE is equal to minus mu m b into d of cos of theta, because mu m and b are constant. They, the magnitude of mu m and b, they are constant, but only this theta is varying here because the dipole moment get rotated in the direction of magnetic field. So theta is the only variable quantity here. This implies that dE is equal to minus mu m b, and then we have minus sine of theta or d theta. If we differentiate this one, or dE is equal to no, there is no minus, because minus and minus that we get plus mu m b sine theta d theta. We call it equation number 2. Now we suppose that now there are many atoms and there are different orientation of dipole moment of each individual atom. Atoms with this kind of orientations are very less in number, and I suppose that let dn, we have total number of atoms is n, dn out of total n. We have total n number of atoms is n, and we say that dn out of total number of n, total out of total n particles have these magnetic axis or magnetic orientation. Axis or orientation. Like I suppose that there are 10,000 atoms in this small material, okay, and I say that only 5 atoms out of this 10,000 atoms have this orientation. So it means that dn is the 5 atoms out of total n, which are 10,000, have this orientation, while rest of the atoms have different orientation. Might be this one, might be this one, or might be this one. Then according to Maxwell Boltzmann distribution law, which says that the number of particles in the energy range, the number of particles in the energy range and the range is E and E plus dE. Is given by this relation dN, the number of particles in the energy range E and E plus dE with this orientation is given by dN, which is equal to e raised to power minus e over kt into dE. Suppose this is equation number 3. Now using equation 1 and 2 and 3, we get dN is equal to e raised to power minus, and e has this value, minus mu m b cos of theta over kt, and then we have dE, which is mu m b sine of theta d theta. This equation can be written as dN is equal to, I will take this quantity outside of this, so mu m b, and then we have e mu m b cos of theta over kt, and we have sine theta d theta. So the final expression is dN is equal to mu mb e raised to the power mu m b cos of theta over kt, and then we have sine theta and d theta, which I can write like this: dn is equal to c e raised to the power alpha cos of theta, and then we have sine theta and d theta. Now this is equation number 4, where we introduce c, where we define c is equal to mu mb, this one, and alpha is equal to mu m b over kt. Like mu m b over kt, I replace it by alpha, and this is equation number 5, and this is equation number 6. Now there are n numbers of atoms, and there are n numbers of particles, atoms having inclination, having orientation, I will say orientation, okay, from 0 to pi. What it means? We have n numbers of atoms, and each atom has their own dipole moment, which are oriented in different directions, okay, and the direction always changes from 0 to pi in this range, like either this one, this one, this one, this one, this one. So the range is from 0 to pi. So it means that we can calculate the total number of particles or atoms with orientation varies from 0 to pi dn by integrating this small factor dn, which is orientation theta. Now using equation number 4, this is equation 7, let's say. Using 4 and 7, we have n is equal to integral from 0 to pi c e raised to the power alpha cosine of theta sine theta d theta. Here, to solve this integral, I can write it as c is constant, so we can keep it outside of the integral 0 to pi e raised to the power alpha cos of theta sine theta d theta. And let cos of theta is equal to x, then minus sine theta, d theta is equal to dx, or sine theta d theta is equal to minus dx. And the limit changes. If theta is equal to 0, implies that x is equal to 1. If theta is equal to pi, implies that x is equal to minus 1. So the above equation now reduced to from 1 to minus 1 e raised to the power alpha x into minus dx. N is equal to c integral from minus 1 to 1 e raised to the power alpha x dx. I remove this negative sign by changing the limit of the integral. If we solve this integral, it's very simple. We get n is equal to c over alpha e raised to the power alpha minus e raised to the power minus alpha, or we get from this the value of c, which is n alpha over e raised to the power alpha minus e raised to the power minus alpha. This is equation number 8. In the next video, I will move forward from this equation. Thank you.